purpose of this lecture, which you'll turn notes in, so you'll want to take notes unless you want to watch it later and take notes. It's your call. I'm just going to do some example problems that are related to the foundations that were in the video that you're supposed to take notes on this week. So this lecture does assume that you've watched that and have some recollection of those ideas. If you haven't watched that yet, you may want to maybe take notes on this later and just kind of observe it, but I will remind you of some things that you would have known before the course versus things that you would have learned earlier in the course versus things that are in the most recent video that's due this week for notes. All right, so we're just going to give some examples and explain how all of this kind of comes together. In fact, this set of problems and the other lectures we'll do before the end of course sort of pull it all together by way of example. So this example here, simple harmonic motion. By harmonic motion, we mean something that oscillates. Harmonic's just a math sciencey word for stuff that goes up and down, back and forth, roundy, it oscillates. Harmonic meaning it can be described by what would be called a sinusoidal function, sines and cosine equations. And so, for example, this equation here, x equals 4 cosine 3 pi t plus pi. So let's just kind of pause for a minute and this equation and think about it. What are the pieces parts? Well, this right here is what we call amplitude. Okay, so on a graph of a function, you know, sine function like this, the amplitude is this distance here, this height. That's what we mean by amplitude. All right. This entire thing right here, this is called the phase angle. And it looks kind of complicated a little bit, but one thing's for sure, whatever the argument, the only thing you can put in a cosine or sine argument, okay, is an angle. All right, that's the only thing that goes in there. You can't put anything else in there, or whatever you're taking the sine or cosine tangent of, that is of an angle. All right, and so this is described as a phase angle, and if time were t, or I'm sorry, if t is time, but if time were 0, then the phase angle would be pi. And so that plus that something times t, that's a frequency, okay, times t. And so you have this right here is the frequency part of the thing, and this right there, that's the phase shift. So these are all things that should have been in your trig or pre-calc course, and they probably were for a brief time as you were drinking from the fire hydrant of knowledge in that course. So those are the pieces parts of this function. And so it's just a math thing that describes that wave, and that wave is useful because if, as we've seen in some of our other labs, we get this shape. A mass on a spring bobbing up and down, over time will produce a curve like this. Okay, and you could imagine if you just put a marker on the back of that mass and rolled a piece of paper by it as it was bobbing, you would see, you'd be stretching that out and you'd get that sine curve. So all this fancy-dancy math for this business here. So I'm going to clear this out. That's just sort of a quick review. What is that equation? Why are you showing that to me? Why are you trying to trigger me with trigonometry? Get it? Trigger. All right. We got to have some math jokes in here. All right. So part A wants to know the frequency and period of the motion. And so right off the bat, frequency, or what we would call angular frequency, we call it angular speed or velocity, but you'll find that what we mean by that is angular frequency. It's number of radians per second. So angular frequency, angular speed, angular velocity, those are all the same thing. And the lingo persists. And so we can read that right off of the given equation. It's 3 pi rads per second. All right. And in some books, you'll even see it written as 3 pi, and it'll be inverse seconds, which I don't like because it obscures the fact that we're talking about radians per second. Is it technically correct? Yes. But it's technically correct because we said so. It's technically correct because we know that any angle measure is a radian, which is we've given a unit sounding name to a unit less thing. Don't ask me, I just work here, all right? I didn't think of this stuff, all right? And if I had, I don't know if I would have done it any different, but anyways. So we just read angular frequency, velocity, whatever you want to call it, right off of the equation. Now frequency there is an equation for that we dealt with earlier and would have been in that trig course as well, and it's just that angular speed over 2 pi. How many times per complete revolution around a circle, which is what 2 pi is as an angle, okay? How frequently does that happen? And so we just take the number that we were given, which was 3 pi rads per second, over 2 pi, and this is going to give us 1.5 what we call hertz. You probably heard that before or seen it on something. It's a frequency. Every radio signal is some sort of kilohertz, megahertz. Your phones are operating on some sort of megahertz frequency. There's all these frequency ranges that we communicate with, electronic waves, waves. The end of this course is all about waves. Because everything ultimately can be described with a wave because everything is vibrating. Every atom is vibrating. Light is understood as a wave. Quantum physics is all about waves, and we can describe all of reality with quantum physics, even if we don't understand what it means. So hertz is just a way to say something per second. All right, so this frequency, in general, we would label it as hertz. Okay, so there's angular frequency, that omega thing, and angular frequency, angular velocity, angular speed. Those are synonymous terms. Then there's frequency. So there's frequency. All right, just the core idea of frequency, which is something per second. All right, and typically it's this angular stuff, but well, pretty much always. So right off the bat, we can determine the frequency straight from the angular frequency that was given in the function itself. But we would have to know, oh, this factor is this, that factor is the other, etc., right? So we have that. Then period, capital T for period, I hope you remember that. It's just 1 over the frequency, and frequency is 1 over the period, all right? And so 1 over that 1.5 hertz, which is something per second, gives us just 2/3 of a second. So it takes 2/3 of a second for this particle that's in simple harmonic motion to have one full cycle. So if it's something that's oscillating vertically or horizontally, it's from here to there and back. If it's something that's actually rotating, it's from this position all the way around back to that position. That's what we mean by a full cycle. And so we can write from, if there's an equation that describes that motion, we can get information directly from that equation about and know things about the nature of this motion. So the math can tell us stuff, but we obviously have to be able to do the math, which is relatively simple, and we have to know what the factors are. All right, so part A, not too hard to do. Amplitude of the motion. Well, that's right off of the equation like I showed. So this is going to be 4 meters, and we get that straight from there. Nothing to compute, just read it from the equation. Okay. Part C wanted to know the phase constant, and that's this thing right here. In fact, one of the ways we symbol it is with this Greek letter phi. Sorry, need more coffee. And it's the phase shift. Remember, it's the shift part of the whole phase angle. Everything that's in those parentheses next to the cosine or sine in other cases, it's the shift away from the frequency time displacement. So both of those are displacements, but they're angular displacements. Frequency times time is the same as linear velocity times time. It's the same thing. And angular speed times time is an angular displacement. So I have an angular displacement plus an angular displacement. And at time 0, there would be this shift of pi. So it's shifted away from just the basic cosine function. Just pushed over. Okay? So here it's right out of the equation. So this problem's really easy. It's only taken the basics of the trig itself. All right, so key idea there. And then this last part is a plug and Chugsville issue. At time equal, so I have x of t, okay, and so at t equals 1/4 second, that means I'm going to have my equation, x is going to be, and it's we know it's a 4 meters out front, cosine of 3 pi times that 1/4 second plus pi. And so this is going to be 4 cosine, and if you do the math, it's 1.7 pi. And in the end, we'll get 2.83 meters. That's the at 1/4 of a second, it's going to be at that position. And at 1/2 a second, it'll be at some other position. Just arbitrarily pick a value of time. Where's the position of this thing going to be? All right. So we want to be able to predict that. So if this sort of harmonic motion is some moving part in a car, if it's a moving part on, I'm thinking of like a hospital scene, because I've just been in one, you like those respirator things. Well, guess what? It's a harmonic motion. It's a cyclical motion. And so we need to be able to make sure that that harmonic motion is at the pace that we want it to be. So we need that thing to be moving at a rate in time that keeps pumping so much air or whatever that thing is. And so somebody on the back end of that device has to code this sort of equation into it so that that actuator moves in time. Or if it's the case that the person who's breathing into the whatchamacallit is what's causing that to move, then guess what? I want to graph that motion, and somebody who understands what the respiration ought, the doctor, there needs to be some sort of reading, and somebody's looking at that and going, okay, that's good or that's bad. We need to do this or do that, or do nothing. And whether they're looking at a sine wave or some other representation of the data, the bottom line, somewhere in the back end, this description is either giving us data or controlling the function. Okay, so life sciences people typically don't have to, they're not the people who are engineering the toys, they're the ones using the toys, controlling how they work. And on some level, small or large, this back-end thinking is part of the puzzle that you need to know. In this case, for that particular example, probably a small part, very small part of the puzzle. All right? All right, so that's that problem. That one's in the bag. Really more of a math review problem that relates to physics than a physics problem. But I chose it for that reason, so we could ease into the ideas. Loudspeaker. Everybody's got one of these. They produce sound by making air wiggle. So subsequent to this lecture, so next week we'll do a lecture on sound. You're going to take notes on one this week about sound, or it's in the box for you to do. And then we'll do problems related to sound, which is more waves. All right, so how does sound work? Good question, I'm glad you asked. If you make air molecules vibrate, they will propagate through space at a very fast speed, 343 meters per second. And so when those air molecules that I'm causing to vibrate by yapping up here, at 343 meters per second, which is really, really fast, you seem to hear what I'm saying instantly from across the room. And that's because air molecules were forced to vibrate in a wave-like fashion, and when it hits your eardrum, somehow your brain understands how to interpret that. And you hear words. And then you say to yourself, wow, that's so amazing. I just love everything that my professor says all of the time, and I wish I could have recordings and sleep to it and listen to it in my car. Nobody's taking me up on, okay, all right, I'll stop dreaming. All right, so loudspeaker. Hey, you got to take a swing, you know. Try to, subliminal messaging, but it wasn't very subliminal. It was kind of like in your face, but all right. Are we recording this? Oops. All right. A loudspeaker produces musical sound by means of the oscillation of a diaphragm. So you've seen them. They vibrate when the music's thumping. Hell yeah, think of our rap stuff. And what's that doing? That's making the air in that region vibrate. And as soon as those air molecules wave off at the speed of sound, the next layer is waving off. And if they're at different intervals, then you have these weird wave pulses and patterns. If you could see it, if you had predator vision or something, and you could see these waves going in big ripples, small ripples, et cetera, et cetera. And then those are going to hit the wall or an ear or whatever. Okay? If the amplitude of oscillation is limited to 1,000th of a millimeter, that's what 1 × 10⁻³ millimeters, what frequencies will result in the magnitude of the diaphragm's acceleration exceeding gravitational acceleration? Okay? So all this problem is here for is for us to get a feel of if a loudspeaker was giving my ear 1 G, the same force that causes me to have weight and everything to have weight. So it's just I don't know if that's good or bad because I didn't think to look it up. Okay? I'd have to convert that to decibels or something, see what, if we go above 90 or 100, that's when it starts to be damaging after some amount of time. All right, so we're told right off the bat, the amplitude of oscillation is limited here. So I know immediately that amplitude is 1 times 10 to the minus 3 millimeters, which, as usual, we need to convert that to meters, and so that's going to be a millionth of a meter. Because 1 millimeter is a thousandth of a meter, and a thousandth of a thousandth is a millionth. All right? And then we always need it in meters. If it's a length, we need it in meters. If it's a force, we need it in newtons. If it's a mass, we need it in kilograms. We always have to make that conversion. Now, in the video that preceded, or in any reading that you would have on oscillatory motion, the maximum acceleration is always given by amplitude times angular speed squared. I actually derived this in the bullet point note video that you're supposed to turn in. And so for now, if you haven't watched that, you can press the I believe button and say that this equation exists. And so the maximum linear acceleration would be related to amplitude and angular speed squared. All right, so there's always some sort of conversion from a linear thing to an angular thing. Doesn't matter what it is, we got a way to convert one to the other. We've done several of those as we've moved along through circular and rotational motion, and now simple harmonic motion, which is just another version of circular motion. Unit circle motion, basically, would be a way to think about that. So that means I can go straight for the angular speed, or which is an angular frequency, okay? And that's just going to end up being our max acceleration over the amplitude, and our max acceleration was 9.8 meters per second squared, gravity, g, and we have the amplitude right off of it's given to us, okay? It's a millionth of a meter, or what we might call a micrometer. Micro is the name of the millionth prefix, all right? And so if I take the square root of all of that, all right, then my angular speed will be 3,130, give or take, radians per second. And the frequency then would just be that omega over 2 pi, that angular speed per complete roundy angle revolution. That's what 2 pi refers to. And if you divide that 3,130 by 2 pi, you get 500 hertz. Now, that is something that you could probably read off of a radio dial or something like that, if you still, nobody has those anymore, everything's digital, and you're dialing into some frequency, but typically it'll say like M, capital M, megahertz or something like that. I'm spacing on that because I just don't listen to a radio. I have my earbuds in with my phone, and so the world has changed, so we have to think of new ways to think of it. But there's some frequency at which those waves are moving, and so if the frequency of oscillation of this speaker is at that frequency, 500 hertz, then that means that speaker is vibrating air molecules fast enough for their time rate of change of momentum to make it feel like gravity on your ears. That would be the interpretation of that. Okay, and so 500. But just think of 3,000 radians per second. Okay, so 500 RPMs, if you want to think of it maybe that way. It's not exactly correct, but it's close enough. That's really fast vibration. Okay, I don't know if speakers can take that or not, but I'm not an expert on loudspeakers. I'm an expert on being annoyed by them. All right, so have neighbors that like to stroll into the neighborhood with their stereos thumping and sit there in their car parking too slowly to go into their house. Not that I'm bitter. All right, let's keep moving through these examples. So the scale of a spring balance. So if you've ever weighed fruit at a grocery store, those are spring balances. Okay, really simple. You know, you put it in there and the little needle wobbles. There's a spring scale in there. It's basically a crude version of the force probes that we use. Okay, but they're accurate. All right. The scale of a spring balance that reads from 0 to 15 kilograms, it's 12 centimeter long spring. So we mess with springs in our mass on spring labs and whatnot, and we could use that spring, we could calibrate it to measure masses, okay, etc. So a package suspended from the balance is found to oscillate vertically with a frequency of 2 hertz. So let's think about this. You're in a situation, I don't know, it's a UPS store, it's something where you're constantly weighing packages or something, and do you want to sit there and wait for it to come to a perfect rest? No, that's a waste of time. So if somebody could build a gadget where you just hang it on there and it oscillates and you get a reading, take it off, next thing. That's what this math and physics stuff would let somebody do. Somebody could easily make a gadget. An engineer would not have to work very hard. This is less than a day's work because it's so simple and straightforward. It's a spring and an equation and a chip that you put some math on, and boom, you get a readout with right answers. Okay? So a professional engineer should be able to do this today. Okay? If they had to make it from scratch and had all the parts available. All right? So part A here. What is the spring constant? All right, so let's remember we have F equals Kx, and X is a thing called stretch. Okay? So at 12 centimeters, a 12 centimeter stretch gives us that 15 kilograms. 0 stretch is associated with 0 mass. 12 centimeter stretch is associated with 15 kilograms mass. Okay? So X equals 12 centimeters. That's the stretch. Okay? Is going to be associated with the fact that we have a weight, otherwise known as mg. So I guess I'm going to, instead of W, I'm going to use F. Okay, we could call it the weight force. Okay, and so we would know that the weight force will be 15 kilograms times 9.8 newtons per kilogram, and that weight force would be 147 newtons. So right off the bat, we can know, all right, this force that's associated with that mass at that stretch is 147 newtons. And why do I need that weight force? Because that's the force that we're talking about in Hooke's law. Remember, F equals Kf is that Hooke's law thing for springs. So I can, now that I know what the force would be at a stretch of 12, I can just solve this Hooke's law equation for that. So I'll have 147 newtons over, well, instead of 12 centimeters, it'll be 0.12 meters. And that means I have 1,225 newtons per meter. So that's our spring constant, 1,200-ish newtons per meter. So I told you that these problems kind of brought it all together, because in order to do this next part, we needed that information from the normal dynamics of a spring, because springs produce oscillatory motion. Therefore, at some level, the harmonic motion of anything that's springy is going to be associated with some force. Okay? And for those returning for Physics 2, we'll spend a fair amount of time talking about the physics of DNA from an electrical perspective, but DNA molecules are springs. They're shaped like a spring. They squish like a spring. They have a spring constant. It's roughly somewhere between 2 and 20 piconewtons per nanometer. They are kind of small. So piconewton's a trillionth of a newton. Nanometers a billionth. All right, so we'll avoid some of the boring typical stuff about electricity and look at things that are more related to the life sciences, biology and whatnot. Anyways, part B, how much does the package weigh? Right, okay. So you may not be aware of it, but I'm going to tell you. There is another equation for frequency as it relates to springs, masses on springs. So I'm just going to give you this equation. I'm not going to derive where it comes from, but it just comes from force equivalencies and whatnot, and the oscillatory motion of things. So the frequency of a harmonic oscillator, a mass on a spring, if you will, would be related to, we have that 1 over 2 pi, so there's always 2 pi is that full roundy revolution thing, but then somehow the spring constant from Hooke's law and mass of the thing that's oscillating show up in this equation. So at least the equation makes sense in the level that it has the right factors. It's a frequency that's related to a complete revolution, and this frequency is related to the things that cause it to be frequent, more or less. That would be a way to think through that equation. Okay? Why does it have those factors? But this is easy. If I want to know how much does the package weigh, okay, then given some frequency. So here's the advantage. Notice that we found that a package suspended from the balance oscillates vertically at 2 hertz. Just data that we know. How much does this package weigh? Well, in order to know weight, you must know mass, because weight is a force that's the product of mass and the gravitational field strength, little g. So we need to know mass. I have an equation that relates frequency and mass. Oscillation frequency and mass of something on a spring. So this equation, either we know it or we can derive it or we can go hunt for it. These are all ways that we go about it. So in order to know the weight, given some frequency of something on a spring, I would first need to know its mass. So if I solve that wonderful equation for mass, square both sides, or multiply by 2 pi, square both sides, divide by blah blah blah, then I'm going to get the spring constant over 4 pi squared frequency squared. So we'll have 1225 over 4 pi squared 2 hertz squared. I'm not going to throw all of the units in. And what you'll get out of this is 7.76 kilograms. Would be what the mass of this object is on this spring with that spring constant oscillating at the given frequency. Which means that I can then compute the weight so 7.76 times 9.8 and you get a 76 Newton weight for whatever this package was, that because obviously a more or less massive package will oscillate at more or less frequency because of the amount of stretch it would put into the spring and therefore the amount of restoring force. So we saw that much just with the things we did. Heavier masses would get that thing moving faster. Lighter masses, not as much. And so the frequency of oscillation, boom. And so all this contraption needs is some sort of motion detector that can know where the end of the spring is or the object itself and know very quickly what the frequency of oscillation is. And given that everything else is a constant, get straight at the mass and therefore the weight of the package. Okay? So this sort of thing, I don't know if like at an airport where they weigh your bag, but this sort of thinking in mathematics and physics connection would be in those sorts of locations where we don't have time to sit there and wait for the thing to come all to rest and be perfect. We put it on there, even if it's still wiggling, and have a good reading and move on. So lots of places, okay? And just think from a medical standpoint, you know, you want information fast in certain situations. You don't have to wait for things to come to rest, or it's, you know, this isn't an academic experiment. We need an answer now. So we need to be able to deal with things that are otherwise, you know, messy data-wise. All right, and this is a relatively simple way to see that kind of approach. All right. So, an electric shaver. Anybody use an electric shaver? I use an electric shaver. Okay. Blades move back and forth. They're tiny little blades over a distance of 2 millimeters in simple harmonic motion. So any oscillation, even if it's along a straight line, is still harmonic motion that has some sort of sinusoidal function to it. And this is happening at 120 hertz, okay, which is pretty fast. Find amplitude, blade speed, etc., etc. All right, so part A here. So what I'm going to call the full swing of this blade is 4 millimeters, meaning moves back and forth over a distance of 2, I'm sorry, I shouldn't say 4 millimeters, 2 millimeters. So a full range is 2 millimeters, okay? What that means is this is double the amplitude, okay? Amplitude's always half of that, so the amplitude's 1 millimeter. So what do I mean by this? So the oscillatory motion of this blade, 1 millimeter up, 1 millimeter down. That's what we would be. So if we were, so think a mass on a spring gave us nice sine cosine waves, and so the movement of mass on a spring no different than this blade wiggling back and forth. So some electric shavers are linear in that sense, where the blade is vibrating along a straight line, and then other electric shavers are like Norelco ones, they're roundy vibrations. These things are spun up in there. All right. So the amplitude is here. This is amplitude. The full swing, okay, of the blade is from 1 meter to 1 meter, or 1 millimeter to minus 1 millimeter. So just kind of understanding amplitude's always going to be half of the full displacement along a line for something. And that's the thing that's weird about oscillatory motion is oscillations are graphed in the sinusoidal wave, which is related to a unit circle, but it's not moving in a circle. But the graph, circular in one sense of the word. So I just want to take time to, I'm just going to erase this so I can keep using this space. All right. So the amplitude, 1 millimeter. Bam. We're done with that. B, maximum speed of the blade. Well, you know already that V equals omega R. Remember? But in this case, that length is serving for that radius part. All right? So this is an equation that is essentially RV equals omega R. We derive that. But our R in this case isn't the radius of a circle. It's the, well, it is. On that sinusoidal graph, that it is pretty much, the amplitude is like the radius of the circle that would go with that graph, even though it's not moving in a circle. And so V equals that, and then omega is 2 pi f for frequency. Okay, so omega and 2 pi f, those are the same thing. So 2 pi times the frequency of 120 hertz times 1 times 10 to the minus 3 meters. Because remember, everything's got to be in meters. All right. And we'll get a speed that's going to be meters per second, because this 120 hertz is a per second thing. It's 1 over second, or s to the minus 1. And so we'll get 0.75 meters per second. So let's think about that. That's 3/4 of a meter per second. Okay, so that far. From here to here. So this electric shaver, the speed of those blades over a really short distance of 2 millimeters, they're moving at almost a meter per second. That's fast. That's why they work well, assuming that the shave guard is right and didn't rip your face off. All right. So one of the things that, so I am sensitive to the fact of, for those physics students that are life science majors, okay, great, why would that matter? And so, yeah, it's a practical application to everyday life for a large number of people. Lots of people use electric razors, or know people that do. So it's a gadget, okay? there's lots of gadgets that are useful in personal and professional life. So guaranteed, some area of life sciences is going to have gadgets. And they're going to have gadgets that have oscillatory motion. Whether it's a razor or some other doodad, it's going to have this sort of feature. And just knowing the magnitude of things that you're dealing with, or having a way to equate that to something in real life, compare it to, is useful. And also that would depend on how deep you go into the pool of a particular life science, how much that matters. If you go to grad school in one of the life sciences, then what I'm talking about in general will absolutely be true for you. All right? So, but practically speaking, for today in this class, it's mainly just a demonstration of, oh, well, I knew it was fast. This gives me a good sense of how fast. Okay, almost a meter a second. That's how fast those blades are wiggling, which is really fast given the small scale that they're wiggling over. All right, but just really fast. You walk. Your walking pace is probably 1 to 2 meters a second. Just normal walking. So this shaver is wiggling as fast as you walk. Then it wants to know the maximum acceleration, and we have another equation that was in the note-taking video. I derived where this equation comes from, but it's another linear to angular or vice versa thing. So omega squared, well, 2 pi f is omega. I can square that. So I'll get 4 pi squared times 120 hertz squared times 1 times 10 to the minus 3 meters. And this will give me 570 meters per second Okay, now we're talking, that's a lot. Divide that by 10, that's 57 Gs. All right? That thing's cooking. That thing's absolutely cooking. Now, I wished I would have picked a problem or made one up that dealt with toothbrushes. Anybody use an electric toothbrush? Okay. One of the things that's good about some of these sonic toothbrushes that are, I think their frequencies are in the thousands, like tens of thousands, is those frequencies kill bacteria. So it's not that they clean your teeth, scrub them any better than manual toothbrushes. I mean, on some level they do because it's a uniform force and you don't press too hard or too light with it. So it's more efficient than manual brushing. But somebody who's just good at brushing could maybe outdo you if you're ho-hum about your sonic toothbrush. But one of the things that you can't get with manual toothbrushing is sonic frequencies that literally kill certain bacteria. If you kill bacteria, then you end the party in your mouth. All right? The nasty bacteria party in everybody's mouth. And so the sonic toothbrush, that vibration, why did they pick it? Because research had shown that certain frequencies will actually kill bacteria. So if I make a toothbrush that people put in their mouth and let it wiggle, then guess what? Brushing can also kill more bacteria, because regular brushing is not going to kill all the bacteria. It's going to clean teeth, it'll wash them out. It's not going to kill them, it's just going to get them out. Get the stuff off of your teeth where they can live, where they go to the party. But now, in addition to getting them off your teeth, you can kill whatever's left behind. That's the basic idea, okay? And so that is a direct connection to the life sciences, okay? The biology of that. If somebody wants to be a dentist, you'll certainly learn about those things and recommend them to your patients, et cetera, et cetera. All right. Now, Next problem. And again, largely my goal here was I wanted to, these things here just give you perspective. It's mainly my main goal in the lecture, because the math is simple. Okay. A tuning fork. I remember when I first started learning guitar 40 years ago, at age 12, we used tuning forks. We even used tuning little pitch pipes. There weren't any electronic tuners now. Like I can clip something to the head of the guitar and pluck a string, it catches the vibration, or my processor, which direct wired in. We don't use tuning forks, but tuning forks, we'd bang it, boom, put to your ear, thump, thump, you know, like that. Now I can do it. There's an app for that. I can sit it right by my phone, my guitar, and get it on my phone. We don't do this sort of thing anymore, but it's a mechanical device. We used to have some. I don't know where they went, but you bang it, and this metal thing, the fork, and it vibrates, and it makes a frequency that you can hear with your ear. And given the density, the metal thickness, etc., you're going to get a frequency. This tuning fork does an A440 hertz or whatever it is. So tuning forks, mechanical vibration of metal sticks, if you will, has simple harmonic motion at a frequency of 1,000 hertz. Okay. And has an amplitude of 0.4 millimeters. So that's really small. That's less than half a millimeter. But you wouldn't expect the tuning fork to have much more than that. Now, the tuning fork that we were talking about a second ago. Find the, again, max acceleration and speed, so we're going to use those same equations again. And then find those things again at a particular displacement. All right, so part A here. We're just going to use the equation we just saw. I know that angular speed is 2 pi times frequency. I was given the frequency of 1,000 hertz in the problem. So I have an angular speed of 6.28 times 10 to the 3 rads per second, or that would be 6,280 radians per second. Okay, so that thing's moving. And we already saw that max acceleration is given by omega squared times amplitude. And so square that number we just obtained, and the amplitude of 0.4, and again it's got to be in meters, okay? So 1,000th of 0.4 millimeters would be 0.4 times 10 to the minus 3 meters, and this gives us 1.6 times 10 to the 4th meters per second squared. So 16,000 meters per second squared. So this tuning fork would be vibrating on a frequency on par with those sonic toothbrushes I was just talking about. But the difference being the battery is mechanically agitating the stick to cause that brush head to do whatever it does. Okay? Versus mechanically hitting a metal prong and letting it vibrate itself away. So there we have the part A, the max acceleration, the max speed. Again, this is just our angular version of V equals omega R. And if you plug and chug those numbers, you're going to get 2.5 meters per second. I'll just, again, the goal of the lecture isn't so much to do every step of the mathematics, especially if it's simple. All right, take that 6.28 times 10 to the 3 times the amplitude, and you'll get 2.5 meters per second. So the ends of that fork, even though they're just vibrating over a tiny 0.5 millimeter or so, that linear speed of vibration is pretty darn fast, especially on that scale. Okay, that's why it's blurry. If you were looking at it, you would see this blurry little vibration. It's because you have this tiny displacement with a huge speed. Back and forth, back and forth, back and forth. So these equations of harmonic motion let us quantify in a way that we can perceive easier the nature of that motion. That is the main import. At least conceptually. Practically, it would be for mechanical control, various reads up. So here, there is a way to part C and D want to know about acceleration and speed at a particular displacement. And so our equation is just literally this one at least. Just morphs into a pure linear form, but amplitude was essentially a linear measure to begin with. So here, if I plug and chug those numbers, I'm not going to bother typing all that in because it's not the most important thing that we're doing. But we'll get nearly 8,000 meters per second squared is the acceleration at that particular displacement of the prong. Half of the amplitude, if you will. That's 10 times less, roughly, almost 10 times less than the maximum acceleration. So it can't have it's not a constant, it's faster here, slower there. Remember the mass on a spring, it's speeding, it's at a small speed, bigger, 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 maximum, then it slows down, then the restoring force brings it to a stop, and then it slowly speeds up at middle, where the spring is at its relaxed length, it's at its max speed, okay, et cetera, et cetera. So going back, think back to our mass on a spring lab. Now this last part, this is a total press the I believe button, okay? So I'm not going to apologize for this, but here you go. This equation, I don't derive it anywhere. I'm just carting it out of our evil equation box and showing it to you. Okay? The magnitude of the speed, in this case, is going to be described by this equation. And I'm not going to bother plugging and chugging it. I'm just going to give away the answer, 2.2 meters per second. If you notice here, at half of the amplitude, okay, we had an acceleration. This acceleration, okay, was smaller by a power of 10 than the max. And this speed at half of the amplitude, where the acceleration was a max, is smaller than the maximum speed at full amplitude. So this makes sense. Yay, the math must at least be in the ballpark of being right. All right. And again, especially on that last equation, we're not going to derive that. You'll just have to trust me that it's a valid equation. Again, this is just illustration purposes. This lecture is just to demonstrate how this stuff applies in things that you can imagine. Okay? Somebody gets paid to do this math. Make things that people will buy, that are safe to use, et cetera, et cetera. And in that process, we learn what limits of this, that, and the other are. We're able to quantify things such as what frequencies would kill bacteria on a sonic toothbrush, blah, 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 that sort of stuff. All right. Mass on a spring. Yay. All right. Done a little bit of this before. Here's an equation. The period. When you're talking about a mass on a spring, we just saw the frequency version of this, which is the 1/ing of it. All right. And so 7 kilogram mass hung from a spring. Vertical oscillation is a period of 2.6 seconds. Find the force constant of the spring. So we need to solve for K. I'll spare you the agony of algebra, which isn't that hard. Square both sides. Solve for M. All right. And so this spring constant . 4 pi squared times that 7 kilograms over the period of 2.6 seconds squared, and you get 40.9 kilograms per second squared. You're like, wait a minute, spring constants are newtons per meter. That's correct. This is equivalent, though, to newtons per meter. And how is that? Good question. I'm glad you asked. Remember, a newton is equal to a kilogram meter per second squared, which, if I just divide both sides by a meter, I'll get newton per meter equals kilogram per second squared. So this equation gives us a really weird unit, it just happens to be equivalent to what we're used to. Okay? I would say that science is littered here and there with things like this, where you do the math and you get this thing that, wait a minute, that's not what I'm used to. It just happens to be equivalent to what you're used to. So we basically did this by a different means in our lab. We did it by regular linear length and force measurements, but we could figure it out based on time that it takes. Because think about it, first zeroth law, every change of position requires a change in time. So that means the period of an oscillation, which requires a displacement, there has to be a relationship that would give us that same thing. And so that's one of the nice things about the physics of oscillatory motion, is that basically it gives us what must be true. If every change of position takes time, then time is a way to understand the kinematics and the dynamics of mass on a spring oscillations. And so this is this one example actually has a lot of scientific import. So let me preach for a little bit. In science, we obtain a lot of facts indirectly. Things that we can't see, but we can see or detect their effects. You can't see time. I can't see atoms wiggle. I can see the results of atoms wiggling. I can see results that are consistent with the theory that atoms must be wiggling. All right, those sorts of things. And so this is one of those backdoor things where I can use an indirect measurement to obtain things. And what we could do is then go take that spring and go, oh yeah, I'll see if this is 41 newtons per meter. And guess what? If you do our experiment, you'll get 41 newtons per meter, assuming the other measures were correct. You know, and so that when we do that, we're like, hey, this indirect measure is valid. Okay, it's accurate to that degree, and so we use a ton of that. And every area of science deals with things that can't be seen, but the effects of what can't be seen can be measured, and we infer backwards to them. So for life science students in physics, it's more about the thinking than it is the math. For engineering majors and whatnot, it's both. The demands on you are all right. This one's a little more complicated. So 2 blocks, a little one and a big one. One's 10 times the other, and a spring. This should be newtons per meter. Typo there. Ranged on a horizontal, frictionless surface so that we don't have to mess with complicated things. So the surface that the big mass is on is frictionless, but the blocks themselves are not. So the top block stays at rest on that bottom block because there's friction between the 2 blocks. So we're going back to the dynamics of friction and then putting it in here with oscillatory motion. All right, so total mass of this system here, this is 11 kilograms, because we got a 1 kilogram and a 10 kilogram thing. So let's just log that piece of data. Coefficient of static friction between the 2 blocks. So right in here, 0.4. So mu up there, 0.4, even though it's frictionless, down on the under the big block. What's the maximum possible amplitude of simple harmonic motion of the spring block system if no slippage occurs between the blocks? So as you can imagine, you could get this thing wiggling so fast that the top block should fly off. So we want to make sure that doesn't happen for some reason. Okay, we need the block to stay at rest on top of the big block. How do we do that? All right. Well, there is this equation that says the angular speed of a spring mass system is in this regard. We're told that the spring constant was 200, and the total mass of this system, that's what that little m in the equation must stand for, was 11. So we have newtons per meter here, kilograms here, and so this will give us 4.26 radians per second, which again, just for grins, you might see written as inverse seconds. That's why it relates to frequency. So now I know the angular speed of this oscillatory motion, which would be related to some sort of linear speed if we knew the radius of motion, which we don't. I don't know how much distance the spring goes through, therefore I won't have an easy time getting the speed of this motion. I don't have enough information to know how fast it's wiggling. All right, so we have that. So now there is the friction between the blocks. All right, and so we do have the fact that the static friction at its max will be the coefficient of friction, static friction, times the normal force, which in this case will be the normal force, the mass of the little block, which I'm going to call lowercase m times g. Remember, normal force is the weight force, mg. All right? So we have that. It's also the case if you recall, the sum of forces have to equal MA. All right? And so all of this together implies that our max acceleration, the sum of forces, is just our maximum static friction thing, and so it's going to be this mu mg over that mass. And so really what I have, the acceleration at its max, is just mu g. This should make some sense, because friction always is related to some fraction of the weight that's pressing into the surface, okay? And in this case, coefficient of friction between these two things, the mass just shakes out as not being material to it. It's just the friction, and gravity is an influencer on that for sure. Now, I have a way to quantify this. What you don't know, but I'm going to tell you, is in oscillatory motion, this is equivalent, the maximum acceleration, we saw this equation before, was omega squared max amplitude. Just press the I believe button. We did that in one or two other problems. So there is an equivalence between the linear acceleration and its angular parts. And so max linear acceleration for oscillatory motion will always be omega squared times amplitude. Okay? So now we can solve this for that max amplitude. And it's just going to be mu g over omega squared. And so we're told it was 0.4 for the coefficient of friction. We got 9.8 for gravity. We computed omega is 4.26. Go through all of this thing, and the maximum amplitude, 0.216 meters. So the most that we can throw it back and forth would be this 21.6 centimeters. All right? So this system with those blocks could go a range of basically 43-ish. So it could go this far. All right? So it could go back and forth from the middle of that. We could have this oscillation, this piston, this whatever it is. And it would keep that thing on top. That's the max amplitude. That would work. So there's this interesting and apparently not that useful, because I'm not aware of people who get paid to make sure that a block sitting on top of another block doesn't slip off. Right? I don't know that I want that job unless it paid really well, so that I could do something and not be bored out of my mind. All right? But we do these sorts of things because there'll be some other application that this template lays on. A mechanical application, it could even be something biological, because even cellular things, molecular motors, etc., they vibrate, they oscillate. Things are on them or off of them. So there's probably a biological version of this on a cellular level, where all or part of the dynamics are the same, even though it's not a mass on a spring. A mass on top of a mass on a spring. But there's something like that. Okay? where this oscillation is just right so that everything else stays like it is, and if the oscillation's not right, everything goes to hell in a handbasket. There's always a parallel to these things. Particle executes simple harmonic motion with an amplitude of 3 centimeters. At what displacement from the midpoint of its motion does its speed equal 1/2 of its maximum speed? All right. So this one, it's not obvious that we need energy, but we're going to need to do energy with this. So max speed at center of motion, okay, and at center of motion, the potential energy is 0. So if you think of a spring, and what this points us to is that the total energy is going to be 1/2 mass times the maximum speed squared. So if you think of the mass on a spring, there's a spot at the relaxed link of the spring where the potential of that spring is 0 because it's not compressed or stretched. There's no restoring force, no potential available for the spring, so its speed is a maximum at that point because the spring has just finished accelerating or decelerating. Okay, so if it's coming from below, it's been accelerated up, the spring stops accelerating, it's at its maximum speed, and immediately the spring starts to compress and slow it down. Potential being added or subtracted in that spring. So this, and I fully admit, there is nothing obvious about the fact that we need to go with an energy approach. But if we did, and we paid attention, we'd say, you know what? There is a spot in this range of motion where the only energy is kinetic, and it happens to be at maximum energy. We had a similar thing like this with the cannonball problem. Same thinking, just a different venue. All right. So we have this fact, and now we're going to leverage this fact. Now at a speed that is 1/2 maximum speed, because that's what this question is dealing with, at what displacement from the midpoint of its motion does its speed equal 1/2 of its maximum speed? I have an equation that deals with the maximum speed. Now I need to somehow relate that to our focal point. All right? And potential energy at that spot isn't 0. It can't be 0 because there's only one spot where potential's 0, and that's at the max speed. So this gets us to an energy balance that says that potential is going to be equal to the total energy minus 1/2 mv squared. Remember, the v in this equation is the v at that other displacement. So the thing that would be easy to get confused and forget is that I have a Vmax, which is leveraging the luxury spot of this is the only energy in town. There's one spot in the motion. Now I'm moving to a different spot in the motion where it can't be the only energy in town, so it would have a different kinetic energy, a smaller one. Okay? Since that's a max speed. So we go through these motions here, and this is 1/2 mass times Vmax squared minus 1/2 mass times, I'm going to put 1/2 of V max in here squared. That way I'll have the same variable. And what this works out to be is 3/8 m times V max squared. Okay, so our potential energy is 3/8 of the maximum, well, we basically have, instead of a 1/2 mv squared for kinetic energy, we have 3/8. Okay, so essentially it's I guess it's 3/4 of the max kinetic energy. That's what this 3/8 would be 3/4 of the max kinetic energy. But since this is on a it's simple harmonic motion, there is a way to understand this in terms of the displacement as though it were a spring. And we have 1/2 m omega squared x squared. So this is basically taking the 1/2 kx squared that you would expect a spring to have, and we're basically angularizing that equation that we saw earlier in the course. So now we can deal with this equivalence that lets us zero in on a displacement. At what displacement from the midpoint of motion does its speed equal 1/2 of its max speed, which we managed to factor into our energy balance. So now if I solve this for x, I will get that. So this is really no more or less complicated than the energy problems we've been working on. It's just, well, I guess it does have a layer of complexity in that the oscillatory motion isn't as straightforward. Okay, I fully admit that. I will not attempt to gloss over that fact. All right, so all of this, this means that x squared, if you the mass drops out, you end up getting 3/4 of amplitude squared, which actually makes some sort of sense, because what did we immediately notice about that 3/8 mv max? That's really 3/4 of mv squared, and that's got to have some sort of relationship to the amplitude. Anyways, this means that x is going to be plus or minus √3/2a, which means it's plus or minus 2.6 centimeters. Which is a reasonable answer given that it's less than the 3 centimeters. It needed to be less than the 3 centimeters. Okay? If it had been more than 3 centimeters, we would have a problem, since that was our max amplitude. So this problem was picked for demo simply to kind of connect it to the work we had been doing with energy and show that that stuff still applies. Here's the thing, and I said it before, there's a way we deal with energy in physics, and it's nice when the energy is like we saw before, it's just a gravitational potential, mgh, or kinetic is mv squared, and that makes things nice. But not everything is that straightforward and simple. As you change context, physical context, then the structure of the dynamics, the energy or force structures change. And then it's just a different math problem. And either you know the equations or you have to look them up. It comes down to it. Very few people just know them all off the top of their head. Even professional scientists end up looking things up from time to time. as opposed to constantly deriving them or pulling them from memory, because there's just too many to know. All right. But obviously, if you're in your lane, you kind of know what's there, and you get used to that, and everything flows off the cuff. All right. We have a few more problems. All right. Simple pendulum. So now the different kind of oscillatory motion. So just something on a string swinging through, clock pendulum, a pendant, or something like that you're just letting it go back and forth. Simple pendulum has a period of 2.5 seconds. What is its length? Well, we have a period equation for this sort of motion. That's a lot like the one we saw before for a mass on a spring, except now it's the length of the pendulum, which is the radius of the circular motion. The length of the string, you got a ball on a string and you're just letting it go back and forth. Well, that length of string is essentially your radius. Okay? And then gravity is what's constraining that motion to some degree. And so basically, if we solve this for L, we'll get T squared G over 4 pi squared. And the plug and chugsville of that, 1.5 meters or so, right? Doing that arithmetic, not important. Now, question is, what would its period be on the moon? Where the G for the moon is noticeably less, 1/6 of Earth. Well, we would take this equation, and T for the moon, well, 2 pi is still 2 pi on the moon. Okay, it doesn't change just because we went to the moon. The length of the string won't change just because we go to the moon, but the gravitational constant for the moon is obviously different. And so this means the period of its rotation on the moon would be, if you see 2 pi, 1.55 meters over 1.67, and you get 6.06 seconds. So everything would go slower on the moon. Because guess what? The rate of acceleration is 1/6 as much. And that relates to something that's heading towards 3 times, okay, the period that it would have on Earth. Okay. We could use a pendulum like this. We could work it around for G, and let's just imagine on a spaceship, you get a pendulum, in a vacuum or something, and you could measure its rate. You could figure, okay, what's the gravitation here? How many G's do I have here? So you could build a G-ometer, if you will, out of some sort of simple pendulum that could take the abuse of whatever environment you put it in, and just work your way backwards to that. So we can find the length of something based on its oscillation. We could find the rate that constrains that oscillation. It's all the math. That's the beauty of the math. We can shift it around to suit what our data is. We can even design something to give us something based on the limitations of our data, etc. Yeah, I skipped one. So here's a simple one. What's the acceleration of gravity at this location? So simple pendulum, 1.5 meter length, 72 oscillations in 180 seconds. What's the acceleration of gravity? So you have a frequency, 72 oscillations per 180 seconds. It's going to give you 0.4 hertz. So frequency. The math of frequency is what you would expect it to be, given what the word frequency means. This many things per this much time. All right? So that many oscillations per that many seconds is going to give me that many hertz. And we also have the frequency equation that we saw once before. Okay, what's the acceleration of gravity at that location? So you solve all of that, 4 pi squared f squared L, and you get 9.47 meters per second squared. So you go up on a really high mountain where gravity is slightly less than what it is down on the ground at 9.8. We could do this with the pendulum. All right. All right. Here you got another ball on a spring. Notice that L cosine stuff. Remember we did that a couple times in our energy problems where that was important to know how to do that. So I'm not going to cover that. So let's see here. I think now that question. Get back into the energy of the system here like we saw in the other one. Simple. So again, this thing, it wants to know about total energy. Part B is dealing with energy. So we'll go ahead and do some energy considerations. It doesn't matter what order we do things in. This means that we could easily do the math here, so I'm not going to bother with plugging and chugging except to say that this is the total energy of the system. Okay, the initial speed that it has, it's all the energy. Okay, at the equilibrium, at that speed at equilibrium. So meaning at the bottom, no potential. Now the potential is going to change as it swings up and back down, but initially all it has is that kinetic energy. So now I know the total energy of the system is all the energy that it started with, which was only kinetic. Okay, we could ignore how far above ground it is because all that's going to matter with potential due to gravity is the change. That's all that's going to matter. So this is our 0 point where it's initially get that speed. Again, not obvious, but true. The maximum Y position is going to be associated with the maximum angular displacement. And so we saw that trigonometry a couple of times in our energy problems and the test on that stuff. And so what this means is that the total this has to be true. Now, I'm going to veer off the path and do some calculus that I even want the life science majors to see whether or not you know it or need to know it is another matter. So I'm just going to kind of little calculus excursion here, mainly because it's a way to get some data that we need. All right. But before we do that, we can take all of this part right here, and I can get cos and theta max. I can solve for that given all the other givens, and I'm going to get 9.03 times 10 to the minus 1 radians, and that means that my theta max is going to be 25.4 degrees, which would be the same as 0.444 radians. Again, skipping math, that's trivial. That's an intermediate algebra equation. You're well past that. All right. So now we have the energy part was given here, and the maximum angular displacement. Right here. So I have total energy, max angular displacement. Only thing I don't have is the period. Okay? And in order to get the period, I need some information that I don't have. I need omega. Okay? Now, omega does happen to be I'll get it here in a second. It ends up being 2.08 rads per second, which means the period is 3.02 seconds. Now, where does that come from? Well, it is the case that the time rate of change initially of the angle is equal to the initial speed over the length. All right, and so this ends up giving us, we were told the initial speed was 2.06, the length is 2.23. This means I get a 0.924 rads per second. So if you're in the college physics class, you don't really need to take notes on the calculus part, okay? And this d theta per dt would be equal to, in a oscillatory motion equation, let me, minus omega theta max cosine of all this stuff we saw at the beginning where we had the phase angle and all this jazz. And so this works out to give us an omega that is our 2.08 here. All right, so it's really short, quick, dirty. It doesn't, just want to give it where it comes from. All right, so for a class like this, we would have needed to give information, more information than the problem statement has. I know that many of you have taken Calc 1, and so you would be able to recognize some of this stuff. Some have not, so you can ignore the black box part and just go with the rest. All right, so again, we can use energy, trigonometry, and obtain things indirectly in that regard. Now the last couple of ones are pretty quick and easy, and we can wrap this up. This will be the longest lecture I've ever given in physics. Okay, heading towards an hour 45. So a physical pendulum, the difference between a physical pendulum and a simple pendulum is subtle, and it's more about a simple pendulum is due only to acceleration due to gravity is all that is constrained, whereas other things are material to this. Again, this equation don't expect you to know it. I'm not going to derive it. Determine the moment of inertia, which is that rotational inertia thing that we introduced last time, or in the last section. And we go through all of these motions of solving for stuff. If you plug and chug all those values, now, I show this merely as a connection to the thing we just finished with. We just finished dealing with rotational inertia in terms of torque, angular momentum, rotational energies, etc., etc. And so this capital I, the rotational mass, if you will, so this is something that's spinning, probably, or oscillating in some other way, according to some pivot. So, and then one last version of this. A disk has a rotational inertia. If we were to go look it up in the book, 3/2 mr squared. Remember, think back to why we even have an mr squared. It's always some fraction of mr squared's difference, sum. It's always an mr squared times something. And the r might be in terms of the length or width or something else like that. So a disk is pretty simple, 3/2 mr squared. We want to find the period for this thin disk with that mass rotating the way that it's rotating. Find the period of this motion. Well, we had this equation from before, 2 pi, or we had a flipped version of that equation, right? And if we plug and chug all of this down, put the I that we have into there, we're going to get 2 pi 3r over 2g. And so our period in this case, so 3 times the 0.2 meters or 20 centimeters that was given, 2 times the 9.8, we have a period of 1.1 second. Right? Again, these last few just demos of how we would pull the stuff from prior work into this framework. All right, and again, we're assuming that you remember some of the old stuff about circular motion, you've familiarized yourself with some of the new stuff, so if you haven't, you might want to watch the other ones first.